Okay, so we are on day 2 of our distance learning journey. So this is your lecture for Friday. If you are starting ahead, cool. If it's Friday, then at least you're on schedule. If you have not taken your chapter 14 quiz on Milestone Say, go ahead and do that because that is due by midnight tonight. So you should do that before you watch new material. So stop this, go take your quiz, and then come back and watch the video. All right, so chapter 15. So we're gonna talk about, this whole chapter is on chemical equilibrium. We've talked about equilibrium before when we talked about our vapor pressure and when things are boiling, and we talked about it with diffusion and effusion and all those things. So we're going to keep talking about equilibrium, but a little more depth and how to calculate it and all that. So our picture here, at the top, we've got a gas and then it's closed. And then if I opened this stopper, the gas is going to fuse so that it's got the same concentration on both sides. Okay, so we've kind of already talked about that a little bit. But we also want to talk about chemical equilibriums when it comes to doing a reaction itself. All right, so many reactions fail to go to completion. So when I say fail to go to completion, what it means is I've got A going to like B. It doesn't mean that all of A goes completely to all of B. So it means that the reactant concentrations stop decreasing and the products stop increasing. So this is supposed to go down and this is supposed to go up, but at a certain point this concentration stops decreasing and this stops increasing because the reaction reaches equilibrium. Okay? So when it reaches equilibrium, it kind of balances out, it stabilizes. So it doesn't necessarily have to mean it has to go all the way. And we're going to talk about what it means when it doesn't go to completion. That's when it reaches equilibrium. That's the whole chapter. All right, now we're going to talk about, is it going to want to go towards the products? Does it want to go this way? Or does the reaction want to go toward reactants? And so the way that we can kind of figure out which direction it's going to go is based on how it's favored. So if there are more products than reactants, this is product favored, meaning it's been pushing to make products. If there are more reactants than products, more of this guy, then it is reactant favored, meaning that the reaction has favored the reverse, going and making reactants instead of products, or the products aren't really forming as much. All right, let's keep talking. Now, when we said that it's an equilibrium, our equilibrium is a dynamic equilibrium, okay? So our reactants can convert to products, but it can go backwards. Our products can react to make reactants. This is where you get this double arrow. So far you've been seeing everything being a single arrow like that. A double arrow means it could go either way. It could go forward or it can go back. It could go reverse, okay? So when we reach an equilibrium occurs when my concentration, not the amount, but the concentration of my reactants and my products stop changing. Not how much I have of each one, but when their concentrations stop changing. Now, this is going to be a dynamic equilibrium. Remember we talked about dynamic before. So when I say that the concentrations stop changing, it doesn't mean that I'm not making products, I'm not making reactants, that nothing's happening. Remember in our vapor pressure in our bottle, and I said some of the liquid is going to come to a gas, and then some of the gases are going to go back down to a liquid, and then the liquid goes back to a gas, and it cycles. But we don't see an overall change, but it doesn't mean nothing's happening. The cycle is still going, but how much is going one way is the same as going another way. That's what we're talking about here. So we're talking about the exact same thing. So in a dynamic equilibrium, we don't see a change. That's why it looks like it stops changing, but it doesn't mean nothing's happening. The species, my reactants, my products, do not stop forming or being destroyed. Okay? So the rate of formation, making my products, the rate of removal, making my reactants, is the same. So how much the forward, the rate of going this way, is the same as the rate of going reverse. So if the forward and the reverse rates are the same, I don't really see a change, and this is why we see that my concentrations are constant. But that doesn't mean nothing's changing. It's just how much is going one way is the same as going the other way. So they kind of cancel out. All right, so let me show you this in a graph, because sometimes it's really hard for people to understand this idea of equilibrium and going both ways. All right, so at the very beginning of my reaction, right here where I have reactants, I got a mole of N2 and 3 moles of H2. That's how much I'm going to start with. Okay, the reaction starts, and I'm going to start making some NH3. So it's going to kind of go like this way and make some NH3. But then it's going to start going back this way, and it kind of goes back and forth. Think about it as like a teeter-totter. It's going to go back and forth until it levels out. Okay? So then it's going to level out and become in the equilibrium state, and I'm going to have a certain amount of each one. Now, how much I have of each one, you can't necessarily just look at the numbers here. Since this is 1, this was 3, this is 2, and kind of figure it out that way. And I'll show you how we figure out how much will be left at equilibrium. But it's kind of a balancing act. All right, here's another example so you can see this. All right, so I start with my cis-2-butene, and I'm going to end with the trans. So just know cis is my reactants, and I'm trying to go to trans. So what happens is I have a bunch of cis. I don't have any trans at the beginning of the reaction. Okay? The reaction starts, cis is going to go away, this is going to go away, and I'm going to start making trans. So I'm losing my cis, I'm making the trans. I'm losing reactants, I'm making products. Okay? So I'm doing the forward reaction. Then what happens is I'm going to have more products, less reactants, but it doesn't mean that it just keeps going. So what you would expect to see is this goes all the way down, this goes all the way up. If we weren't reaching equilibrium, if we were going to completion, you would have all of your trans, you would have none of the cis. But this reaction doesn't go to completion, and most don't. Okay? So most of the reactions are going to do what we're doing in this chapter. That's why there's a whole chapter on it. Okay? But when you think is happening, all the cis goes away, all the trans goes. What happens is the cis goes, the trans comes and is made, but it isn't a completion. I don't lose all of the cis and I don't make only trans. It's going to even out and balance out at a certain point. Okay, so let's look at this. So what's going to happen is as they do this, as they balance out, and they get to this equilibrium where they flatline. Now they're at equilibrium, so there's no change in my concentration. It's staying steady. So now we can see that the rate going forward is going to be equal to the rate reverse. My rate going in the forward direction is going to be the same as the rate going in the reverse direction. Okay? Now we can rewrite this. Remember, rate is going to be equal to K times your concentration of whatever it is that you started with. So I could rewrite this. Instead of it being rate, I can say that we know that rate is equal to K times concentration of A and B, etc., right? So for my forward reaction, this is going to be K, and my reactant here is the cis. And we want to notate, let me change this, let's change this to K forward, and then cis. Or you can say KF if you want. And then the rate reverse is K reverse. And then if I'm going this way, my product is what I'm actually reacting. So it's going to be the trans here. So, and we can use the stoichiometry, that it's a 1-to-1 ratio, and that's how we get the 1 here and the 1 here, because this is an elementary reaction. Okay? So the isomerization is elementary. So we said K forward times the cis is equal to K reverse times the trans. Well, let's rewrite this. Let's put my K's on the same side. So let's move this that way. And let's put my concentrations, move this over there. So K forward divided by K reverse is equal to trans stays here divided by the cis. So I got my concentrations together and my K's together. This ratio of my K's to my concentrations is called my equilibrium constant. And we're going to be solving for this a lot this chapter. This equilibrium constant, the symbol for it is a capital K, lowercase c. The C stands for concentration because I'm plugging in the concentrations. So you can see it here. My Kc is the forward divided by the reverse, which is also equal to my trans divided by my cis. Another way you could think about this is the products, this is the reactants. And this is going to be equal to some number in a certain temperature. And we'll talk about what that means later and how it's affected. But we're going to get a value at a certain temperature. These constants will change when I change the temperature. So here's this constant, and as my temperature increases, my K changes. So that means that equilibrium constants, these Kc's, are going to be temperature dependent. So my Kc's are going to be temperature dependent. So that's why anytime you see a problem and you see a Kc value, you're also going to see a temperature associated with it because they have to post that. They have to tell you what the temperature is with the K because the K can change based on temperature. Just like with density when we did that, how if you got the density, they also had to put the temperature because they just have to report it accurately. Okay? So don't get thrown off by that. So let's talk about how do we write this equilibrium constant in general. So if I give you a reaction and I say write the equilibrium constant. So here my A, my B, my C, and my D, those are my coefficients for my reactants, A and B, and for my products, C and D. So Kc is equal to K forward divided by K reverse, which is equal to, that's the same thing we had here, forward and reverse, and it's going to be my products over my reactants. Okay? So my products would be the concentration of C to whatever this coefficient is, times the concentration of D to whatever that coefficient is, over A, concentration of A to his coefficient, times concentration of B to his coefficient. So the way you want to think about this is products divided by reactants, okay? And it's raised, the powers are based on these stoichiometric coefficients, okay? All right, so let's practice this. So I want you to write the Kc's for this. Now, most of the time when we write the Kc, we don't write this because we know that it's K forward, K reverse. Most of the time, it's just this part and this part, okay? So let's look at this. So I want you to write the Kc, the equilibrium constant, for these two. So we say Kc is products over reactants. So products, reactants. So I write whatever this is in a bracket, NO, and then this becomes my power. Whatever this is, it's a reactant, so it's on the bottom. Since this is a 1, I don't really write the 1. Then O2, since it's a 1, I don't write the 1. So that would be my Kc. Not too bad, right? So products over reactants. All right, let's do the next one. Kc is equal to this guy in my bracket, because remember, brackets mean concentration to the squared, second power. then N2O4, and there's a 1, so do the first. So that's my equilibrium constant. All right, so let's look at doing a problem. If all the equilibrium concentrations are known, it's easy to calculate Kc for a reaction. So let's see. Consider 2A goes to B. At equilibrium, A is 2 molar and B is 4 molar. What is Kc? So we got a problem. First thing we want to know is what is Kc? So what are we looking for? We're looking for our Kc. Okay? Then let's write what do I have? So they gave me A. It says at equilibrium. This is going to be important. So I want you now to start writing it's at equilibrium, because when we start getting more advanced, we're going to get initial and final conditions also. So I want you to start writing if it's initial an I, if it's final an F, and if it's equilibrium just EQ, just so that we can get practice doing that. Okay, B, equilibrium, is 4 molar. All right, and I have my equation. So first let's write out my generic Kc. If I'm trying to find Kc, I need to write out what my Kc is. It's not necessarily an equation, more like a process. So I need to start writing it out. So my Kc is my B, because it's products to the first, over reactants, A, squared. That's a bad squared. There we go. All right, so then if I want to solve for Kc, do I know the equilibrium concentration for B? Yep, right here. Do I know the equilibrium concentration for A? Yep, right here. So I plug it in. This is 4. This is 2 squared. So this is just 4 divided by 2 squared is 4. So we get 1. Now, there's no units. So the Kc is just 1. You might think molar divided by molar squared. We're not worried about all that. There are technically units for Kcs, but we just want to know what the number means, what the number stands for. Okay? So we're not going to stress about exactly what the number is. All right, let's do another one. Let's determine Kc for these 3 equilibrium mixtures. So I've got mixture A, mixture B, and mixture C. You can't see it here, it says A, B, and C. But mixture A, B, and C. So I want to know the equilibrium. So let's first, if I'm trying to find the Kc's, let's write it out generically. So Kc is my product. Here's my product. So trans over my reactant, cis. Okay, my trans over my cis. All right, so let's look at it. For A, do I know how many trans I have? So if you look here, it's color-coded. So cis is green, trans is purple. So cis is green, trans is purple. So we want to go down here and we want to count them up. So if you count them up, there are 1, 2, 3, 4, 5 green. And there are a total of 50. So I'll let you know so you don't have to sit here and count all of these. There's a total of 50 dots. So if 5 of them are green, because that's easier to count, then that means the other 45 are purple. So that gives me 9. So now I have my Kc for A. Let's do B. Kc is, it's going to be my purple over my green. That's kind of a lot. So just pick one of the colors and count. And so if we count the green again, got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25. So we got 25 green. So green we said it's a cis, so 25 green. And if there's 25 green, there's 25 purple. So that gives me 1. And then let's do it again. But I got less purple, so let's count the purple. 1, 2, 3, 4, 5. I got 5 purple. Purple is trans, that goes on top, 5. And if there's 5 purple, there's 45 green, which gives you 1/9. So I've got my KC for A, for B, and for C. So all it is just looking at it and plugging it right in. All right, so we're gonna stop there just because I don't want the videos to get too long. And we're gonna pick up on what these numbers mean. So what does it mean if KC is 9 versus 1 versus -1/9? And what does it mean if it's, you know, a bigger number versus a fraction, those kind of things. So we'll talk about that on the next lecture. Have a great day. Don't forget, Chapter 14 quiz.